So in the video on stationarity, we also talked very briefly about integrated series. An integrated series is a series that is not necessarily stationary, but as the sample size increases, as t increases, does converge to a long-term mean, variance, and level of autocorrelation. Now, we talked about integrated of order 0. Sometimes we have a data series where this does not happen, so it does not converge, it remains non-stationary also as t increases. But when you take first differences, where you don't look at the effect of x on y, but a change in x on a change in y, then that series might be integrated of order 1. And if that is the case, if the impact of a change in x on a change in y asymptotically as t increases has a long-term mean, variance, and autocorrelation, then we call that first differences relationship integrated of order 0, and the original relationship between y and x integrated of order 1. And we can also have integrated of order 2 or 3, where you need to take differences in differences to get to an integrated of order 0 series. A typical example of non-stationary data is related to prices or money. Prices or inflation, etc., they are not stationary time series. They don't revolve around some kind of long-term mean. They go up and down as depending what happens. But that doesn't mean that there's no relationship between those variables, right? So we can have income and interest rate and demand for money, and these variables, they will be related to each other, even though each of them are not going to be stationary. So economists have worked out the following equation. That is a complicated multiplication and with exponentials and so forth. But if we take the log on both sides, so we take the log of m on the left and the log of this equation on the right, we end up with an additive series where we have different variables logged and where we can run a linear regression. And most of the variables in this regression are non-stationary. They evolve over time. What we need, however, for the regression model to work is the errors to be stationary. In what case that can happen? If we have a proper equilibrium model between a set of non-stationary variables, we can very well have a situation where even though they're all non-stationary, the error is stationary. And if this is the case, we call that series co-integrated. That means that a series of variables that are themselves integrated of order 1 or 2 or something like this, together are integrated of order 0. And if that is the case, we can run the regression normally and we can interpret the results. In fact, when we then regress y on x, whereas originally with non-stationary data we had a major problem, with co-integrated data, that is integrated of an order higher than 0, but together the error term when you model them all together is integrated of order 0, is super consistent. It converges very quickly. The data set does not have to be large. It converges very quickly to the right data. But if they together are not co-integrated, but the residuals are integrated of order 1, then the regression is spurious, and that is the most problematic we can have. So co-integrated data, particularly good. It's super consistent, converges very fast to the right answer. Not co-integrated but still integrated means that we actually have a spurious regression. We get highly significant results that are completely false. So very important to properly test. So if you regress two non-stationary variables on each other, there's a very high chance that it's a spurious regression, that they correlate because they both change over time, without there being any connection between the two variables. But if they are co-integrated, so they are non-stationary time series, but they have a structural relationship to each other, and when you run a regression, the residuals are stationary, then they are co-integrated, and we have a model that is super consistent. The data set, the estimates converge to the right estimates very quickly with a relatively small data set. So it becomes crucially important to properly test whether the two non-stationary series, or more than two, are co-integrated or not. And for that we have the Engel-Granger testing procedure. So that is a testing procedure for co-integrated of order 1. So assuming that the two variables are integrated of order 1, and once we run a regression, the residuals should be integrated of order 0. They should be stationary. So the two steps you take are a test on x and on y separately to confirm that they are of integrated of order 1, for which we can use the augmented Dickey-Fuller test, the ADF test. Then we regress x on y, and we look at the residuals, and we perform an ADF test on the residuals to confirm that those are stationary. And because of the fact that the residuals are not observed but are estimates of the underlying errors, we have slightly revised critical values, and when we use those we call this the angle Granger test. And this idea that we discussed earlier of two variables having a structural relationship to each other, and when an x changes, y will have a new equilibrium value given the x, but it will take time to adjust, and there is a gradual adjustment each time period from where y is to the equilibrium value given x, the error correction model. This model is closely aligned with the idea of having two series that are co-integrated, that change over time, that are not necessarily stationary, but where the residuals are stationary because there is this structural relationship. So if we take the example of prices and demand and money, which is a co-integrated series, we can then also calculate the short-term and long-term elasticities that we discussed. As long as the errors are not autocorrelated, OLS is consistent and efficient. If the errors are correlated, there's a moving average process, you cannot get away with OLS, you will need a maximum likelihood estimator. In R there is the IREMA package. And if any of the variables is not stationary, the model needs to be reformulated first. So by reformulation, I mean looking at first differences, for example, to get from an integrated of order 1 to an integrated of order 0 series, or test that the non-stationary series are co-integrated so that jointly they are stationary. The residuals, when we look at the structural relationship between the two non-stationary variables, is stationary. And then we can apply OLS, because then they are co-integrated.